Okay, we're looking at homework solutions for chapter 10, the gas chapter. So the first problem is that you have some carbon dioxide gas. The pressure is at 56.5 millimeters of mercury. It's in a 125 milliliter flask. You transfer the gas to a new flask, and the new pressure is 62.3 millimeters of mercury at the same temp. What is the volume of the container that you transferred it to? So here we can see that the pressure changes definitely, and presumably the volume changes. But since the gas is transferred to a new flask and it doesn't say that gas was lost or gas was added, the moles of gas are constant, and it does say the temperature is constant. So here, this means that you want to use this equation, P1V1 over N1T1 is equal to P2V2 over N2T2. Now, this equation is not given in your book, but I give it to you because this is Boyle's law, Charles' law, Avogadro's law, combined gas law, Gay-Lussac's law, all combined into one. And the beautiful part of it is we don't need to know the name of the law to use it correctly. So the way to use this law is as follows. If something doesn't change like the moles, it just drops out of the equation. If the temperature doesn't change, it drops out of the equation. So we end up with P1V1 is equal to P2V2. And then when we rearrange and we get V2 is equal to P1V1 over P2, and we just plug in the numbers and solve. So you can see the units cancel here, and we're left with milliliters. Easy peasy. So we're going to see that again for this problem. We have a sample of gas at 135 milliliters, 22.5 degrees Celsius. Pressure is 165 millimeters of mercury. What is the pressure when placed in a 252 milliliter flask at 0 degrees Celsius? So you see here, I'm making a list. I've got my P1, V1, T1, N1, I don't know what that is, but the sample of gas is placed into another flask, so N2 is equal to N1. So that means we're going to use this equation, P1V1 over N1T1 is equal to P2V2 over N2T2. And since N doesn't change, we take that out of the equation. We're solving for the new pressure P2, so we get P2 is equal to P1V1 times T2 over V2 T1. Oh, and I forgot my 2 here. So P1V1 times T2 divided by V2 T1. So we plug our numbers in. P1 is 165 millimeters of mercury. V1 is 135 milliliters. And T2, you'll notice, is 273.15, not 295, because this is T2, not T1. That's where people usually make the mistake in a problem like this. So V2 is 252 milliliters. And then we have 295.65 K. So there's the setup. The K's cancel, the milliliters cancel, and we'll be left with millimeters of mercury. And if we estimate the answer, we might say that 273 divided by 252 is about 1. We might say that 165 goes into 295 about 2 times. So 2 will go into 135 about, I don't know, 70 times. So the answer might be around 70-ish. All right, so let's take a look and see what the answer is. You can see from my 3 significant figures here, 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 my 4 significant figures here and 4 significant figures here that we get 3 significant figures when we're done. So 165 times 135 times 273.15 divided by 252 and divided by 295.65. And I get 81.7 millimeters of mercury. Okay, so I would expect to see some work like that. I'd expect to see that. And there you go. Number 3, ethane burns in air. What volume of O2 is required for complete combustion of 5.2 liters of C2H6? What volume of H2O is produced? Same pressure and temp. Now, you know that PV equals nRT. And in a particular case like this, where the pressure is constant and the temperature is constant, so you can think about this whole thing is being done at room temperature. When it begins, it's at room temp. When it's done, it's at room temp. And the pressure is 1 atmosphere. So all of that is constant. When those are constant, that means that the volume is proportional to the moles, because we know that R is also a constant. So in this particular equation, or situation, I should say, the volume is proportional to the moles. Now, normally when we look at the coefficients, these are moles. 2 moles reacts with 7 moles to give you 4 moles and 6 moles. Under this special condition where the volume is proportional to the moles, we can say that this is 2 liters reacts with 7 liters to give you 4 liters and 6 liters. So the coefficients under this situation are also ratios of volumes. So when they ask what volume of O2 is required for complete combustion of 5.2 liters of C2H6, we start off with 5.2 liters of C2H6 and we multiply by 7 liters of oxygen over 2 liters of C2H6. That's how easy this problem is, okay? If we did it another way, it would just be a pain in the butt. I'll show it to you just once. Okay, 5.2 times 7 divided by 2, and we get 18 liters of O2. And that's the answer. So let's do it the long way, shall we? So the deal with the ethane is that we know that we've got 5.2 liters. We've got 5.2 liters. Let's see, what else do we have? That's it. 5.2 liters. We don't know what the pressure is. We'll just call it pressure. We don't know what the temperature is. We'll just call it temperature. And we don't know how many moles that is. We'll just call it moles. And here, I'm going to call this the pressure of ethane, the temperature of ethane, and the moles of ethane. And we have 5.2 liters of ethane because that's ethane. So to be able to use this equation, if we want these to be moles, we need the moles of ethane. So we're going to say P of ethane times V of ethane is equal to the moles of ethane times R, the temperature of ethane. Now R, we don't have to put E on it because R is always the same no matter what the gas is. So the moles of ethane are equal to P of ethane, the volume of ethane, over R and the temperature of ethane. So that's the moles of ethane. Now, if I want to get the moles of O2, I would take all of this and I'd multiply by 7 moles of O2 to 2 moles of ethane. Okay. So there's that. Now, this again, this whole, well, how do I say this? I'm just going to go back to here. I'm going to cross this off. So that's what we have so far, that the moles of ethane is equal to this. Now, if we want the moles of O2, we have to start with the moles of ethane and multiply by 7 moles of O2 per 2 moles of ethane. And these two would cancel and we would get moles of O2, right? So that's how we figure out how many moles of O2. Well, this is the moles of ethane, so I'm going to write down PeVe RTe is equal to 7 moles of O2 over 2 moles of ethane. And that makes more sense than what I have above. So this is the moles of O2. Now, what do I do with the moles of O2? Well, I use that the P of O2 times the volume of O2 is equal to N of O2 R T of O2. All right. So we want the volume of O2, which is equal to the moles of O2 times R, the temperature of O2, over the pressure of O2. So what is the moles of O2? Well, it's this right here. So I'm going to write down pressure E, VE, oh, this should be times RTE times 7 mole of O2 over 2 mole of ethane. All of this times R, TO2, and PO2. Now, in this problem, they say that it's the same pressure. The pressure doesn't change. So that means that these pressures actually cancel because they're the same pressure. The temperature doesn't change. So these also cancel. And here we have the R's, they cancel. So the volume of O2 is simply going to be the volume of ethane, which happens to be 5.2 liters, 5.2 liters of ethane times 7 mole of O2 over 2 mole of ethane. And we're going to find out that these moles actually cancel, so to speak, and the E cancels when we're left with O2, and you get 5.2 liters of O2. I should have left these off because it's just really just a ratio 7 to 2. 7 O2 to 2 ethane. So there's the answer that we get, 5.2 times 7 over 2, which happens to be 18, excuse me, which is the same answer we got here. So what's the lesson you want to learn here? It's pretty simple. If the pressure and the temperature are constant, the coefficients are moles or pressure, or volume. And if the volume or temperature is constant, then the coefficients are going to be pressures. So you can work that either way. All right, it's late, so I'm getting a little tired here. Let's see if I can keep it up. Here's number 4. Balloon holds 30 kilograms of helium. What is the volume if the pressure is 1.2 atmospheres and the temperature is 22 degrees Celsius? Now, almost always, when you are given a problem like this and you have given a mass, you want to use the density formula. So density, which is equal to mass divided by volume, is equal to PM over RT, where this is the molar mass. Now the book shows you how this equation is derived. I'm not going to bother showing that to you. This is mass, and this is volume, temperature, and pressure. So we want to know what the volume is if we have 1.2 atmospheres and the temperature is 22 degrees Celsius. So basically we want to use this part of the equation, and we're going to use that the V is equal to MRT over PM. So we have 30 kilograms, and we know that 30 kilograms we could write instead as 30.0 times 10 to the third grams. Okay. And we know for R, we're going to use one R or the other R, depending. 22 degrees Celsius is going to be 22 plus 273.15, which is 295.15. So 295.15, but this is only good to the ones. So I'm going to put a little arrow there. And for the pressure, we're going to use 1.20 atmospheres. And for the molar mass of helium, we're going to use 4.01 grams per mole. So which R do we want to use? We want to use the 0.08206 liters atmospheres per mole per K, because this is the R with atmospheres, and we want the atmospheres to cancel. Now the grams will also cancel. The moles will cancel. The Ks will cancel. And we're left with liters. So if we wanted to estimate our answer, all we have to do is say 1.2 times 4 is 5. 5 goes into 30 6 times. 6 times, I'm going to call this 0.1, is 0.6. And 0.6 of 295 is like saying 6 times 0.6 times 300. So 0.6 times 300 should be what, 180? So we get 180 times 10 to the third. That's a large volume. So let's see what we get here. 30.0 second EE3 times 0.08206 times 295.15 divided by 1.2 and divided by 4.01. And I get, oh geez, a big number like I expected. I'm changing my calculator scientific notation, so get 1.51 times 10 to the 5th liters. So that's a pretty big balloon for 30 kilograms of helium. But I guess that's what's to be expected, because we're talking about what, 30,000 grams of helium. So maybe that's not a big balloon. So it'd be nice if you showed me this equation to begin with, and then this, and the final answer. Okay, we have a 0.0130 gram sample of gas with the empirical formula C4H5, and it's placed in a 165 milliliter flask with a pressure of 13.7 millimeters of mercury at 22.5 degrees Celsius. What is the molecular formula of the sample? So this is another equation where we see a mass. So that makes me think I want to use this equation here. Okay, so here we're solving for the molecular formula. So we're going to say that the molecular formula is equal to mRT over PV. Okay, we do have a pressure, we do have a volume, we do have a temp, and we do have a mass. So we put a 0.0130 grams for the mass. Here, since the pressure is millimeters of mercury, I'm going to use the 62.37 millimeters of mercury per mole K for my R. And for my temperature, I'm going to say 22.5 plus 273.15 is 295.65. The pressure is 13.7 millimeters of mercury. And the volume is 165 times 10 to the minus 3 liters. I can replace that M with a 10 to the minus 3. Okay. If I wanted to estimate this answer, I could try a number of things. 165 goes into that 2 times. 2 times 62.37 is like 120. 120 divided by 13 is about 9. And 9 times 0.013 is going to be like 0.09 if I ignore the 3 part. So instead of 0.09, maybe we call that 0.11. And then, of course, when we take that 10 to the third and put it up here, that becomes 0.1 times 10 to the third, which is 1 times 10 squared, which is 100. So I'm guessing the answer is that the molar mass is around 100. So let's see. 0.0130 times 62.37 times 295.65 divided by 13.7 and divided by 165 second EE negative 3. And I get 106. And what are the units here? Well, millimeters of mercury cancel. K's cancel. Liters cancel. Gram does not cancel. And mole does not cancel. So this says that the molar mass is about 106 grams per mole. So what is the molecular formula? Well, we know that the molecular formula divided by the empirical formula, the molar mass of these, when you divide these, you get a multiplier, is what I call it, right? And here, we know that the molar mass of the molecular formula is 106. What is the molar mass of this? Well, we have 4 times 12 plus 5, which happens to be what? 53. So our multiplier is 2. So here, that means that we have 106 grams per mole divided by 53 grams per mole, which is equal to 2. So that means we take our empirical formula, multiply it by 2, and we get C8H10 for the molecular formula. So I'd want to see all of this work here for a problem like this. And that's number 5. Number 6, a scuba canister has potassium superoxide, and it reacts like this with CO2 to make a potassium carbonate and more oxygen. So what mass of potassium superoxide reacts with 8.90 liters of CO2 at 22 degrees Celsius at 267 millimeters of mercury? So the first thing I'm going to do is I'm going to solve for moles of CO2. Then I'm going to use that to solve for moles of the per superoxide. Then I'm going to use that to solve for the grams of the superoxide. So how do we solve for the moles of O2? Well, we're going to use PV equals nRT. How come I'm not using that fancy equation P1 V1 over N1 T1? And the answer is because the volume of CO2 isn't changing, the temperature isn't changing, and the pressure isn't changing. So the moles of our CO2 is going to be PV over RT. The pressure is 767 millimeters of mercury. The volume is 8.90 liters. The R, we're going to use the 62.37 millimeters of mercury per mole per K. And for the temperature, we're going to use 22.0 plus 273.15, which is 295.15 K. Okay, so we can see the K's cancel, millimeters of mercury cancel, the liters cancel, and we're going to be left with moles for an answer. And this, again, is going to be moles of CO2. If we want to estimate this answer, we could do it a number of ways. I guess what I'll do is this. 62.37 goes into 623.710 times. So it should go into that about 12 times. So 12 times 10 is 120. 120 over 295 is about 1/3. So the answer should be about 0.3. Okay, let's see what we get now. 767 times 8.9 divided by 62.37 and divided by 295.15. And the answer is 0.37. So my 0.3 was a little low. And I get three significant figures, but that's how many moles of CO I have, or CO2. So to get the mass of KO, I'm going to take my 0.371 moles of CO2, multiply by 1 mole of CO2 on the bottom, and 4 moles of potassium superoxide. And then I want to multiply by the molar mass of potassium superoxide. So how much does a potassium weigh? It weighs 39.10. 2 oxygen weighs 32.00 for a total of 71.10. So times 71.10 grams of the superoxide per 1 mole of the superoxide. And if we estimate this answer, this is about 1/3. So 4 times 71 is what, 280. 1/3 of 280 would be about 100. So let's see what we get here. So I'm going to take this number times 4 and times 71.10. And I get 105 grams of potassium superoxide. So naturally, I'd want to see all this work here for a problem like that. Okay, 7. Calculate the RMS speed for carbon monoxide molecules at 25 degrees Celsius, and what is the ratio to that of argon at the same temp? So this is the formula for RMS speed. So that's what this whole little thing means. And it's the square root of 3RT over the molar mass. Now, that is the molar mass in, let's see, I want to make sure I do this right. This is the molar mass in kilograms per mole, okay? And the reason I know it's in kilograms per mole is because this is the unit for R, and this J is equal to kilograms meters squared per second squared, okay? So here, if that's R, and you're multiplying that by the temperature, and here, since we have that, that's part of R, I should say, and then we also have the K in the mole. When you multiply by the temperature, that's going to cancel the K's out. And here, when you have this divided by kilograms per mole, that will cancel these kilograms out, and these moles cancel. And then when you take the square root of meters squared over seconds squared, you get meters per second. So we got to take that molar mass and turn it into kilograms per mole. So we know that carbon dioxide is 12.01 plus 16.00 for 28.01 grams per mole. Let's convert that to kilograms per mole. So that would be 1 kilogram per 1,000 grams. So we get 28.01 times 10 to the minus 3 kilograms per mole. Okay, so now we're ready to plug all the numbers in. What is the speed? 3, 8.3144598 joules per mole per K. And the temperature at 25 degrees Celsius is 298.15 K. And then all of this over the molar mass, which is 28.01 times 10 to the minus 3 kilograms per mole. Now, since we have this as kilograms per mole, we know we're going to get meters per second over here. So I'm going to plug this all in by first starting with square root. So I've got the square root. No, I don't. So I've got square root. I'm going to put 3 times 8.3144598 times 298.15 and divided by 28.01 second EE to the negative 3. Okay, and if we wanted to estimate this answer, how would we do it? Well, let's see. I'd probably do 8 times 3, or 3 times 300 is 900. 9 times 8.3 or 900 times 8.3, kind of hard to do, but if I say it's 9 instead of 900 times 8.3, well, 9 times 8 is around 72. We'll call that 75. And then I can add the zeros in and say, well, that's 7,500. Now, 7,500 times 10 to the minus 3 becomes 7,500 times 10 to the plus 3. So 7,500 divided by 28, well, 28 will go into 75 about 3 times. So we got 300 times 10 to the third. So this is going to be a pretty fast molecule here because we're taking the square root of that. And I'm going to call this 330 times 10 to the fourth. And the reason I'm going to do that is that becomes 10 squared when I take the square root. And the square root of 30 is going to be what? 5 or 6. So 5, 6 times 10 to the 10 times 10 squared. So let's see what we get. And I get 5.1. Looks like I have 3 zig figs there, so that's the limit. So I have 5.15 times 10 squared meters per second, so about 515 meters per second squared. Now, what is the ratio to that of argon at the same temp? Well, to do that, I'm going to pull out another piece of paper here. And we're going to say that the root mean square speed for argon at the same temp, so here this is going to be CO, compared to the root mean square of argon is going to equal, well, 3RT over the molar mass of CO divided by 3RT, the molar mass of argon. So we want this ratio right here. So we're going to clean this side up. When we clean this side up, what we get is 3RT over the molar mass of CO times the molar mass of argon over 3RT. So I did 2 things at the same time. When I have this under the square root and this under the square root, I can combine both of these to under one big square root. And then when you have a fraction divided by a fraction, you take the bottom fraction, flip it around, and multiply it times the top fraction. So you can see all this cancels out, and we get this really nice formula for the RMS speed of CO over the RMS speed of argon is equal to the molar mass of argon over the molar mass of CO. And we take the square root of that. So what is the molar mass of argon? It is 39.95. And that's grams per mole. And the molar mass of CO we know is 28.10 or 0.01 grams per mole. So 39 divided by this is like saying 4 divided by 3, which is 1 1/3. So what times what gives you 1 1/3? Something a little bit bigger than 1, right? Because 1 times 1 is 1. So something a little bit bigger. So let's do this one now. I'm going to clear. I'm going to do my square root. And I'm going to do 39.95 divided by 28.01. And I get 1.19. So that is the ratio of the RMS speeds, 1.19. So what does this mean? This means a 1.19 moles of CO per hour versus maybe 1 mole of argon per hour. Or it could be per second, or it could be per year. I don't know, but this is the ratio of how fast. Okay, so that's number 7. Let's see, number 8. This is a tough one. So this compound diffuses at a rate of 17.7 milligrams per hour. And this diffuses at 15.0 milligrams per hour under the same conditions. And they want to know what is the molar mass of this UFX and what is its molecular formula. Okay, so the problem with this diffusion rates are that they are grams per time. The rates must be moles per time or liters per time. And that isn't either. So what we're going to do here is we're going to take these rates and we're going to turn them into moles per time. So for I2, when we look at the rate, we're going to take our 15.0 milligrams per hour and multiply by 1,000 grams per 1 milligram, just to get rid of the milligram. Boop. And then we're going to multiply by the molar mass of I2, which is 126.90 times 2. So that's 253.80. That should be on the bottom, 253.80 grams per 1 mole. All right. Now, I already know that this is going to get a little complicated, but I want you to look at that number right there. If we say that the molar mass of I2 is 253.80 grams per mole, then this is 1 over the molar mass of I2. So I'm going to multiply instead of all of this by 1 over the molar mass of I2. And you'll see where that gets me in just a moment, but let's clean this up a little bit. So what is this rate going to be? It's going to be 15.0 times 10 cubed over an hour and the molar mass of I2. And we also have the grams will end up canceling out of here. We can go ahead and leave that in though, if you want. Okay, so what is the UFX rate? Well, it's going to be 17.7 milligrams per hour times 1,000 grams over 1 milligram, and then times 1 over the molar mass of UFX, which cleans up to 17.7 times 10 to the third grams per hour and over the molar mass of UFX. So now you can kind of see why I did that above is because, well, I don't know the molar mass of UFX. So I just have to use a variable for it, and there it is. Okay, so that's the start. Now, what do we do with this number and this number? Well, this is the rate of I2, and this is the rate of UF, or UFX. All right. So do you remember this formula here where we do the RMS speed? So here, if I do the RMS speed of I2 over the RMS speed of UFX, that's going to be the molar mass of UFX over the molar mass of I2. Now, this RMS speed is essentially the rate, and this is the rate. So if we look at the rate of I2, we had 15.0 times 10 to the third, and that was grams, over hour times the molar mass of I2. So that's what that is. Now, what was the rate or for U Fx? Well, it was 17.7 times 10 to the third grams hours times molar mass of UFX. Okay, so you can see when this cleans up, the hours cancel, the grams cancel, and we get, I'm going to go ahead and flip this and clean this up. The 10 to the thirds cancel, and what this ends up being is 15.0 over the molar mass of I2 times the molar mass of UFX over 17.7 is equal to the molar mass of UFX over the molar mass of I2. All right, so let's clean this up a little bit. Let's go ahead and take 15 and divide it by 17.7. And we know that answer is going to be around 0.9 or 0.8, right? So here we get 0.847. So we get 0.847 times the molar mass of UFX over the molar mass of I2 is equal to the square root of the molar mass of UFX over the molar mass of I2. We're going to square both sides. So that means I have to square this, square this, square this, and square this. So when I square 0.04847, let's see, square it. Where's my square? There it is. So here I get 0.718 molar mass of UFX squared over the molar mass of I squared is equal to the molar mass of UFX over the molar mass of I squared. So when I have the square root and I square it, I get what's underneath the square root. Okay, so we can see what's going to happen here is that one of these is going to cancel with one of these, so I'm going to do that. One of these is going to cancel with one of these, so I'm going to do that. So we get the molar mass of UFX is equal to the molar mass of I2 divided by 0.718. We know the molar mass of I2 is 250, let's see, what was that? 253.80 grams per mole divided by 0.718, and we get that the molar mass of UFX is equal to close to 300 or so, right? So let's see what that is. So I'm going to divide it by 253.8, and then I'm going to take the inverse. And so I get 353 grams per mole for UFX. Okay, so that's the molar mass. What's the formula? Well, to get the formula, we have UFX is equal to 353 grams per mole. And that's going to be to a U plus an F plus an F plus an F plus an F all the way until we get to 353, right? Well, how much does a U weigh? A uranium weighs 238. So one of these is 238. So that means if we take our 353 minus our 238, we've got, let's see, minus 238, we get 115 left over. So all these fluorines have to equal 115, and each fluorine is 19. So I can say that the number of fluorines times 15 has to equal, or times 19, I'm sorry, has to equal 115. Let me just write that out over again. The fluorines times 19 has to equal 115. So the number of fluorines has to be 115 divided by 19. And let's see what that ends up being. It ends up being 6.07. So we've got 6 fluorines. So that means the formula is UF6. Boom. So that was a pretty tough one. And that was the toughest one we've had to face so far. In the book, this is one of those triangle problems, which means watch out. Okay, only 2 more problems. If 12 grams of O2 is required to inflate a balloon to a certain size at 27 degrees Celsius, what mass of O2 is required to inflate it to the same size and pressure at 5 degrees Celsius? This sounds like an interesting problem. Let me think about how to do this. Okay, when I see the grams here, that makes me want to use the idea that density is mass divided by volume, which is PM over RT. Okay, I don't know why I want to use that, but I do. Okay, so here in the first situation, if we look at this mass under the first situation, we've got 12 grams. We've got a certain size. We don't know what that is, so I'm going to call that V1. And we've got a certain pressure. I don't know what that is. The molar mass is going to be 32. R is going to be whatever R is. And the temperature, it says, is 27 degrees Celsius. So here, for the first set of conditions, let's see, what's going to be the same about both of these? The pressure is the same in both cases, right? The molar mass is the same in both cases. So I'm going to do this. The PM is equal to MRT over V. Let's see if I did that right. Yeah. So for the first set of conditions here, we have this idea here. The pressure is the same. The molar mass, well, here, the mass is 12 grams, R is whatever, T is 27, and V is, V is the same size. So I'm going to do this. PMV is equal to MRT. So this doesn't change whether it's in the first condition or the second condition. All right. So here, if I look at PMV under the first conditions, it's MRT. Under the second set of conditions, PMV is equal to MRT. So I'm going to call this the mass under the first set of conditions, the temperature under the first set of conditions. This is the mass at the second set of conditions, and this is the temperature at the second set of conditions. Okay, so they're both the same pressure, they're both the same molar mass, and they're both the same volume. So that means that M1 R T1 is equal to M2 R T2. And now I see that the R's cancel out, so I get the mass of 1 times T of 1 is equal to the mass of 2 times the T of 2. So what mass of O2 is required to inflate it to the same size at 5 degrees Celsius? I would say that, well, the mass 2 is mass 1, T1 over T2. Now, what is mass 1? 12.0 grams. What is T1? Well, T1 is 27 plus 273.15, so that's 300.15 K. And what is 5 degrees Celsius? Well, 273 plus 5 is 278.15 K. Okay, so what is my answer going to be? Clearly, this is a little bit more than 1. 1 times 12 is 12, so the answer might be 13, 14, something like that. So let's see what it is. 12 times 300.15 and divided by 278.15. And I get 1.2, excuse me, not 1.2, 12.9 grams. So we would need 12.9 grams to inflate it to the same size and pressure at 5 degrees Celsius. And it's pretty clean, pretty clean. So the only thing that I would have altered is I would have said PMV over R is equal to M1 T1. And the same over here, PMV over R is equal to M2 T2. And therefore M1 T1 equals M2 T2. Kind of a clever way to figure that one out. Okay, 10 looks like a tough one. You got a container of helium, 3 liters at 145 millimeters of mercury, separated from a container of argon that's 2 liters at 355 millimeters of mercury. When you open this valve up, the gas is mixed, so you get helium in this side and helium in this side, and argon in this side and argon in this side, like we show over here. So the question is, after you allow them to mix and equilibrate, what is the partial pressure of helium? What is the partial pressure of argon? And what is the partial pressure total? Or excuse me, the pressure total. The way to do this is pretend that you have helium, 3.0 liters, 145 millimeters of mercury, and here's your closed valve, and here's your other container. And in this container, you have nothing. So when you're done here, what's going to happen is that the helium will then mix into both containers. So we're working just with the helium and seeing what happens to the helium. This is a P1V1 over N1T1 is equal to P2V2 over N2T2. So if we look at just the helium, we have P1V1 over N1T1 is equal to P2V2 over N2T2. Now the temperatures don't change, so they drop out. The moles don't change, so they drop out. So to get the new pressure of helium, we do P1V1 over V2. Now P1 is 145 millimeters of mercury. V1 is 3.0 liters, and V2 is the sum of these two volumes, which is 5.0 liters. So let's see what we get here. 145 times 3 over 5 should put this close to 100 or a little less, right? Okay, times 3 and divided by 5, and we get 87 millimeters of mercury. So that's what would happen to the helium if we just let it spread out. Its overall pressure would be 87. Well, that happens to be the answer to the partial pressure of helium. So we do the same thing for argon. So I'm going to put argon here. We've got P1V1 is equal to P2V2. So P2 is equal to P1V1 over V2. And instead of using these values, we're going to use the ones for argon. So the pressure is 355 millimeters of mercury. The volume is 2 liters, and then over 5 liters. So 2/5 of 355 should be a little less than a half. Half of this would be about what, 170? Is that right? 100, yeah, 170-ish, so maybe 150-ish or 140-ish. Let's see what we get. 355 times 2 divided by 5, and we get 142 millimeters of mercury. So that is your pressure of argon in the new container. So what is the pressure total? Well, the pressure total is 87 millimeters of mercury plus 142 millimeters of mercury, which puts us at 9 to 212 millimeters of mercury. So this problem seems like a tougher problem than it really is. You just treat each gas as if it were the only thing in there, find out its new pressure, And then you add all the pressures together because of Dalton's law, which says the pressure total is equal to the pressure of the individual gases. Boom. All right, thanks for listening. Long video, but there's your answer key.